So this is the confusing part in this chapter. Okay, a lot of students get lost basically understanding the difference between static pressure and stagnation pressure, right? And realizing that the stagnation pressure is basically a reference state. It's kind of a label. No, it doesn't have to be always there. Okay, it's just that if you take the flow and stop it, it will go to its stagnation pressure, right? So in this example, basically, or this slide, I'm showing you a wind tunnel. That's where they basically test, you know, small vehicles or big vehicles depending on the size of that wind tunnel. The point is, inside that test section, you'd like to get really very high velocity V test section, all right? So how do you do this? You put a fan over here and you suck the air. The air will come from outside, go through this thing, subsonic flow. The area will get smaller and smaller. As a result, the velocity will increase, right? Achieve V test section. So you can go from V equals 0 over here to V equal V test section over there. This is all because the fan is pulling the air out, right? So the air from this point to that point, until he touched the fan, he basically was under its own energy. The fan didn't touch it yet, right? The fan didn't give him any extra energy. So one can easily apply Bernoulli equation between 1 and 2. And basically say that at 1, the velocity, which is almost 0, and the pressure, so P, atmosphere, or P1, let's call it P1, will be equal to the velocity at 2, half rho V2 square, plus the pressure at 2. Right? Isn't that Bernoulli equation between 1 and 2? So because V2 built up because of that reduction in the area, what happened to the pressure? The pressure will drop, right? That pressure, P2, the pressure here in the test section, is that static pressure or stagnation pressure? Static. It's very confusing name. It's a conspiracy to confuse undergraduate students that they call it static pressure. They should call it P moving. That would be a perfect name, you know. What's P moving? And you would say, well, it's that number. Because that's the pressure of the moving air, all right? Which considerably is lower than P1, right? P1, that's the pressure of the stagnant air. So that's a good name, right? So that's P1 is the stagnation pressure, right? If the air have 0 velocity, you will get P1, the high value. And B2, that's P static. Why it's so low? Because, well, the velocity is moving now. You take some of the... But if I take the air over here, if I take a sample of the air over here at that velocity and manage to slow it down, turning all the kinetic energy into pressure back again, what will happen to the pressure? It will increase again, right? It will increase again. If you stop it isentropically, no losses, no heat transfer, nothing is lost, nothing is added, you go back again to be stagnation, right? So the confusing part of the student that the students always miss is that during this passage here, during this flow in this nozzle, if I ask you at this place, what is the velocity? You don't really know. It's something between 0 and V this section, right? He's accelerating. But if I ask you what is the stagnation pressure at this point, you should tell me it is. What is the stagnation pressure at this point? Let's call this point A. What is the stagnation pressure at point A? It's P1. It's still P1. And what is the stagnation pressure at point, say, B over here? It's still P1. So all those points, while he's accelerating and his pressure, his static pressure is dropping, his velocity is increasing. During all this time, he still have the same stagnation pressure. If I go and measure the pressure over here, will I get P stagnation? No. I will get a static pressure that, depending on the velocity at that place, I will see it drop. Basically, the pressure will start dropping from P atmosphere over here to this guy. But all those time, it has one stagnation pressure that you cannot measure it, but if you take that air and slow it down isentropically, he will shoot up to his stagnation pressure. So it's really as if his stagnation pressure is kind of his label, right? Or basically kind of, let's imagine I'm worth $1,000. I then can basically go and get an iPhone, $500. Now I have, how much did I say? Let's call it $500, okay? So $500 iPhone and $500 cash. But what's my net worth? Still thousands. Because I can sell isentropically I can give this iPhone to Bob and he will give me $500 for it. Nothing will get lost from the value of the iPhone if I trade it back. Nothing can get lost from the kinetic energy if you slow it isentropically. Right? So, and then I can get a wallet, another $100, 500, 100. So you can keep basically changing but the net worth is still the same. So the stagnation, let me get my cursor. So the stagnation pressure during all that journey, is still the initial value. What will make my value drop from $100? The phone will get broken, things will get broken for me. So what will make, then I'm not worth $100,000 anymore, right? So what will make that B stagnation drop from us? Friction at the wall. So later in the course, when we start having friction at the wall, we cannot assume that nothing is lost and you still can peak all the way up to B stagnation. No, your B stagnation will drop for every centimeter you are going into a ductless friction. Alright? But as long as the duct is isentropic, B stagnation remains the same all the time. Alright? This is a big deal, okay? Because students keep, until the end of the course, they keep saying, what is the stagnation pressure at that place? They are talking about the test section. And they don't see that it's the same stagnation pressure we started with. Simply because the flow in this is assumed isentropically. Okay? Again, in real life, if the friction is really small on that area change, the friction itself is small, yeah, you can go ahead and assume isentropic. And you can assume B naught remain the same all the way. So I want to stay in this slide forever until you get it, because this is very important. So if anyone is confused why the stagnation pressure does not change, while the static pressure, the actual pressure, the moving pressure, is dropping, ask me now. So the static pressure is dropping because the area is changing. The static pressure also could increase if the area is increasing for a subsonic flow, while the stagnation pressure remain always the same.
Because it's only the still air.
Because it's kind of the reference state. It's like basically assuming that taking that pressure, moving pressure, or the static, well, let's call it by its name, the static pressure, taking that static pressure and that velocity at that place, or that place, or that place, every one of them, if you take those guys, put them together, you go up to B stagnation. You go anywhere and you sell all your stuff, you still get your $1,000.
And it stays the same until you get to the fan, correct?
Excellent. Why?
Because it hasn't changed. It hasn't been affected.
No. Why it will change in the fan?
Because then it's being added to.
Right. Then you basically, and guess what happened to the fan? The fan pushed B static to become B ambient, right, or B atmosphere, or B, right, so that it can actually get it out. You cannot send the air out when he's having this very low pressure. He's being sucked by the fan up to the fan point, but then once he leaves the fan, he's supposed to go with his static pressure need to be above B atmosphere so that he can get out. So that make his stagnation pressure higher than, of course, higher by its kinetic energy, right? So the fan basically makes sure that B static. So before the fan B static is negative, that's fine because we are sucking the air. But once we kick him outside the fan, you need to have a static pressure that's equal to the room he's leaving to. All right? That's confusing part. Let's not think about this. Forget about this part. Just think about the inlet section. During the inlet section, B stagnation remain the same because you take that kinetic energy, you take that pressure, put them together, he will shoot up to his stagnation pressure. assuming nothing is lost during that journey. Personally, when I was undergrad, my problem with that was I just didn't buy that there is a point where V is 0. Because I used to tell my TA that, well, if V is 0, then that air is not moving to us. And like if he is going to come to our wind tunnel, he needs to have a point 1. And he told me, well, just go a little bit further, or consider a point a little bit further. I told him, still, it has to have a velocity, otherwise it will not come. The point with 0 velocity and B atmosphere will never come to us. Why you are even telling us about that point? But of course, you know, at the limit, when V gets smaller and smaller and smaller, you will hit B stagnation, right? So B stagnation is really the limit as V gets smaller and smaller and smaller to become 0. Okay? Life was very confusing when a person was undergrad. It will get better, I promise. All right. So in this slide, he basically explained the difference between stagnation property and static property. All right. So by the way, in this course, stagnation and total, they are the same. When I say stagnation pressure or total pressure, it's the same thing. And when you look at the example and you say B naught or B total, they will call it B total like this or B total like this. They are all the same thing. It's all the same thing. Just some books call it total, some books call it stagnation. We are talking about the same thing. It's the pressure when the velocity is 0. By the way, there is also stagnation temperature. And there is static temperature. What is the stagnation temperature? Well, that if you slow the air also to 0, if the air velocity go to 0, his temperature will go up or go down. What do you think?
Go up.
Excellent. Why it will go up? So the air is moving and he has a temperature. That temperature, for I don't again why they call it like this, but it's confusing. They call it the static temperature. The static temperature is not the velocity of the, sorry, it's not the temperature of the stopped air. The static temperature is the velocity of the moving air.
Temperature of moving air?
Yeah, it's the temperature of the moving air. And the static pressure is the pressure of the moving air. They just call it again static because you have to be that's what they give you in the textbook. They tell you because to measure it, you have to be static with respect to the air. So you take your probe, temperature thermometer, and you run with the air, basically. Then you will be measuring the static temperature. But if you stop the thermometer like this in the wind tunnel, if you stop the thermometer like this, the air will have to stop at the tip of the thermometer. That's the stagnation temperature. You are measuring the temperature of the non-moving air, the stagnating air, the stagnation temperature. Right? So anytime you hear static temperature, it's actually in your head, tell yourself, the moving air temperature. The static pressure, that's the moving air pressure. Right? So now, again, if we slow down that moving air, we will hit stagnation pressure, stagnation temperature, stagnation enthalpy. All those property over here, when V equals 0, B total, T total, H total, those are all stagnation property. All right? V, B, T, H, those are the moving property. Let's call them, according to our book, the static pressure, static temperature, static enthalpy. Fortunately, there's no static velocities. You just call it velocity. Right? Right. That would be horrible. Static velocity? And what is that exactly? Right? Okay? So just one more thing that to hit B total, you have to stop the air without any friction. You have to stop the air isentropically, no friction. But to get the T total, it's a little bit easier. Friction is okay, but you cannot allow any heat transfer to leave the ducts. So the condition on the temperature, it's only to be adiabatic. So even if you stop it with friction, that's okay. What will the friction do? The friction will just take the kinetic energy, make it heat. So anyway, you will get your stagnation temperature, whether you stop it isentropically, without friction, or with friction. That's easier on us, right? Merit of the story, the end, The take-home message is that there are static property and there are stagnation property. All right, very good. So he's basically, over here is basically showing us that if we stop the air as adiabatically to start with, you apply the first law between 1 and 2, between moving and non-moving, between the static property and the stagnation property. So here is the first law over here. Of course, neglecting potential energies. There's no potential energy when it comes to gases. It's very little. We always neglect potential energy. Liquid is different. So you apply the first law between 1 and 2, and you got h plus v squared over 2, and you got h1 plus v1 over. Of course, the velocity here is 0, and that h2 is h total. And at 1, that's the v1 and the h1, or basically the static property. So then, by definition, h total is h plus v squared over 2. Or basically, the stagnation temperature is the static temperature plus all the energy, all the kinetic energy, all the meter per second square turn into basically heat. That's what will turn static enthalpy to stagnation enthalpy. Okay? So now when we take as ideal gas, basically we say H is CBT and H total is CBT total. Stagnation enthalpy, stagnation temperature. Static enthalpy, static temperature. Then you divide the whole thing over CP and you can prove that T total is T plus V squared over 2CP. This is not important. What's important is the next equation. So you can take CB and write gamma R over gamma minus 1. Okay, you write it over here, and then you multiply by T over T, that's okay too, right? And now what you have is gamma RT, that's A. And you can take this T and T out, and you'll end up with this relation. This relation is the most, I guess, the second most important equation in this course. After A equals square root of gamma RT that we had in chapter 2, now you have the relation between T static and T stagnation, or total temperature. Again, total temperature and stagnation temperature, they are the same. So you can see what Sean said, that was right, that when you basically have kinetic energy, some moving air, that will make T total higher than T static. Because all this kinetic energy represent, if you stop them, they will shoot up the temperature, right? So this is the relation between T total and T. And as you can see, it's function of Mach number and gamma, and that's it. In the exam, sometimes this equation is like, you don't want to plot gamma minus 1 over the calculator and make m square, and so it's sometimes you just need, for different m and different gamma, you just want the results without even taking the time to hit the calculator. So they had this equation for us in appendix at the end of the book, and that's appendix B. Let's open appendix B 1, and let's make a, so for say m equal 2 and gamma 1.4, tell me what is T total over T?
For which?
M equal 2 and gamma equal 1.4.
M equals 2, T over T naught is 0.5556.
Say that again.
0.5556.
0.556. So I wrote it 1 over 0.556 because Bob said it's T over T naught. T is smaller than T naught, so I was asking for T naught over T. So then it's 1 over this, right? So that table is much faster to use than the equation, but the equation is always accurate. You can always use the equation. All right? The table appendix B actually have not just B1, there's B1, B2, and B3. What's the difference between B1, B2, and B3?
Gamma value.
Different gamma for different gases. So, depending on the gas, you will basically be able to jump between one table to the other. Right? So you have 3 tables for 3 gammas. Those tables in the quizzes and the exams, don't interpolate them. Right? To go faster, that's the point of using the table. So when say I tell you what's the Mach number, let's jump over every 0.2, right? Is that correct?
Yeah,
What's the jump?
0.02.
0.02.
0.02.
So basically you just pick the closest 0.02. So if I say 0.03, you are free to pick 0.02 or 0.04. Alright? So don't interpolate in the table. Now in the homework, however, you can afford to actually spend more time, especially that there is this software that I uploaded for you. This software is uploaded to Desire to Learn under the homework section. It's called Compressible Property, I guess, or Comprop 2. It's written by our Professor Gajar with his co-authors. And that software is basically all the tables in the book for chapter 3, chapter 4, chapter 6, chapter 7 is here actually, and chapter 9 and chapter 10. Together also with design of airfoil. So for example, chapter 3, what we did right now, what we said Mach equal to, right? And the gamma 1.4 is here. If you want to change the gamma, change over here. And just hit enter. And that's T naught over T, 1.8. So the 1 over the 0.556 is 1.8. So that's T naught over T. And P naught over B, we'll find it in a second. But you can also pick from the graph. You can just basically, the x-axis is the Mach number, and you can basically just move like this. And so in the homework, we expect more accuracy from you because you have access to this, right? And it will make your life much easier than just using the table. Question about this? In the exams and the quizzes, just use the table and don't interpolate. Very good. So that's our stagnation temperature and our static temperature. Static, stagnation, right? Again, I'm calling it total, but total and stagnation is the same.
He said you can use that.
All right. So there is also, remember when we said when the flow is going through isentropic process, there is a relation between the pressure and the temperature ratio. That was from chapter 1. So P over P is basically T over T, gamma minus 1. Well, we know what's T total over T. Then we can get what's P total over B. And so the P total and P relation is almost like this, except for what? The exponent, the gamma minus 1, because of this. Right? That's the only difference. It's the gamma minus 1. Okay? So that is the difference between B total and P. So in one of the homework problem, he's basically giving us let's look at it. So he said a beta static tube placed in a subsonic airflow, the static pressure and temperature are this. Those are the static value, P and T. The difference between the beta and the static pressure are measured using a manometer. So he means the difference between the total pressure and the static pressure. The beta hole stop the air. So that difference, the 200 millimeter of mercury, the rho GH of mercury, is B total minus P static. And you would like to find out the air velocity and the Mach number. And will the results be different if incompressible flow is assumed? So before today's lecture, you could have used, because we had this in the previous homework, remember? First homework? We should have used this. And at that time I told you this was the last time you're going to use it. So if you cannot use this equation to get the velocity in the wind tunnel between B total and B static, what are you going to use? You're going to use this one. Right? So will the results be different? Yes. This is the accurate one. This is the approximated one. So you can prove mathematically that this is this when the Mach number becomes 0. Mach number becomes 0 not because V is 0, then there's no problem. Mach number becomes 0 mean because that the A is much, much bigger than the V, to the extent that the Mach number is very, very small. Okay? So how can you prove this? If you basically expand this polynomial, if you open this, and then take the limit as m go to 0, you will show that this is exactly will end up being this. Right? So this equation is valid when the Mach number is very small, and this one is valid all the time. Subsonic, supersonic, anything. This equation is always valid. Right? Questions? So now we understand the difference between B static and B total, right?
Absolutely.
Very good. So now we have those two equations that are available in Appendix B. T naught over T and B naught over P. All right? Note that the equation, this was confusing one time for a student. So the equation is T naught over T, but the table is T over T naught. Not a big deal, just flip either one of them, right? Flip either one of them, you get exactly the same number. So what did we start with in this chapter? We started by saying that we want to solve an area change. If we have different area, we would like to know what's the new Mach number, what's the new temperature, what's the new pressure. We didn't do this yet. But we needed those stagnation value because that's how we're going to write the solution in terms of. So before I continue and I show you how does the area control pressure, temperature, and Mach number, let me ask you, if I have this rocket engine nozzle, and that nozzle, that's converged divergent nozzle, is isentropic, can be assumed isentropic. And I start with P naught over here, say 100, let's call it 500. 500 kilopascal, and T naught, say 500 Kelvin. What would be P naught and T naught here, just before we leave? Excellent. Right? You get it all? It will that P naught and T naught throughout this nozzle is what we started with. But what is the pressure and temperature? And they vary from one point to the other, depending on how quickly they are moving. What's the Mach number at each place? So each place will have his own Mach number, and will have his own B static and T static. But they will all those points across the nozzle will have the same P naught and T naught. This is really the essence of this chapter. If you don't get it, let's ask me again.
Would that be because we're not actually adding heat, as the heat's been added prior to the nozzle?
Excellent. Because this nozzle is isentropic. Isentropic means there is no heat transfer, adiabatic, and there is no friction on the wall. So because of this, nothing is being lost. So he can speed up and his pressure drop or increase depending on whether he's subsonic or supersonic. He can do anything he wants. But he still got the $100 on him. All right? So, 1,000. We said 1,000? 1,000. He still got the $1,000 on him at every location. All right? But we are very close now. All we need, because I gave you T naught over T and P naught over P, and I'm telling you T naught and P naught remain the same throughout the nozzle, all you need from me right now to finish this chapter is a relation between the Mach number and the area. And we are done. Because if I tell you, here is a relation between the Mach number and the area get 2 times bigger, the Mach number get 5 times bigger, you just take this new Mach number, plug it in here, and get the new temperature and new pressure. Right? Note that at the beginning of the nozzle, when the flow was coming from this huge reservoir, huge chamber, really big, the V here is almost excellent. And the pressure is P naught, the stagnation pressure. So in the reservoir, because the velocity is so small, the pressure is almost, the static pressure is also the stagnation pressure, because V is 0. All right? And T is T naught. So when the problem say the reservoir pressure and the reservoir temperature at the beginning of the nozzle is this much, you should also think this is the stagnation pressure and the stagnation temperature. Right? Because the area is so big, the velocity is really small. When I was working in my postdoctor in Wright Pat Air Force Base, we actually, the big tank where the pressure and temperature is there is not in our building. It's actually across the street from our lab. And so the flow basically come to us in a really big, it's big pipe, but still not really infinitely big. I mean, and you can see it coming across the street, basically, the pipe coming to us. So the pressure that we receive in our lab, is that B naught and T naught? When it first crossed our wall, is that B naught and T naught? Why? If I put a pressure gauge on that section, you know, when the flow just come into our lab, and then you go into our nozzle, and then it becomes supersonic. We were testing at Mach 2 at that time.
When it comes out, it still has velocity, so it hasn't gone to the stagnation pressure yet.
Right. So Bob is right. The pipe coming into our building, let's imagine the pipe is coming like this. This is the pipe coming to our building, and then I send it to our nozzle. This pipe, it has a velocity. So the pressure here is not stagnation pressure, right? The stagnation pressure is much higher than that pressure. You get that stagnation pressure if you slow down that air, right? Because that's the pressure of the moving air. It's much faster. That pressure is much higher than what I'm going to get if I actually send it to my smaller nozzle. Okay, but it's not the stagnation pressure and stagnation temperature because it's moving. Okay. So 1 year in the midterm, the problem was like this, that they are used to basically telling them the reservoir pressure and the reservoir temperature is this. And so you always take this as the B naught and T naught. We are done. But in 1 year, the exam said the flow start with a pipe basically this much. And he gave you the area. He didn't say infinitely long. He said it's 10-inch diameter. And here is the pressure and temperature in that pipe. Are those the stagnation value? Those are the static value. What if I want the stagnation value out of them? What should I do? I use this equation and this equation, right? Then I can take that temperature with that velocity or Mach number, I can get my stagnation temperature. Now I know the stagnation temperature in that pipe. All right, good. So let's see an example first. This is basically on basically understanding what is V stagnation and what's V static, the difference between them. So I said airflow at Mach 0.25 through a pipe with 6 centimeter diameter. Stagnation pressures, he said right now, those are the stagnation pressure of the flow, right? Somehow he managed to measure them. Taking a sample and slowing it down as entropically he got. So those are the stagnation pressure and the stagnation temperature. And he gave us gamma 1.4, okay, and it's air. And air behave as a perfect gas with constant specific heat. What he wants from us, he said calculate m dot. So in this pipe, we have T total, P total, and the Mach number. Can anyone give me m dot?
It's going to take me a second.
M dot is, you want to know how many kilogram per second are moving into this pipe. Help? Anyone? Density multiplied by rho EV, right? M dot is rho EV. So rho EV, what do I need? What do I have in rho EV? I know the area, right? Rho EV. So do we have the area? Because we have the diameter, so pi over 4, right? We get pi over 4 out of it. Do we know the velocity? Mach number multiplied by square root of gamma RT. That's our quest today. So yeah, I got the Mach number, right? But I don't know the T. And the same problem happened when we come to the rho. The rho is, what's the rho? What's the rho? That's the gamma. What's the rho? The density, what's the density, guys, for air?
I
Huh?
want to say 8.314, but that's not it.
Wait, density? We have to find that from the ideal gas cell.
Excellent. Who said that density 1.2, that was fluid 1, forget this. Density is not 1.2 anymore, okay? 1.205, that's the fluid 1 stuff. What is the density? B over RT. That's the density. So now, I have the same problem here. I don't know the temperature, I don't know the pressure. Well, I thought that we were given the pressure and temperature. Isn't that right? Were we given the pressure and temperature? Stagnation. We were given the stagnation pressure and temperature. And when it comes to the V, and when it comes to the density, are those the stagnation or the actual actual pressure and temperature in the pipe? Right? The static, what they call them, the static pressure, which what I really call the moving pressure and temperature. Right? So I need the static, and I was given the total. So how can I turn from the total
Those two formulas.
those two formulas or
Or the tables.
the table at the back, which is exactly those two formulas. So let's do the table because you can use the equation. So if I go to the table at Mach what? Mach 0.25
0.25.
and gamma 1.4, can anyone give me what is T over T naught and B over B naught?
Well, since it's in the middle, it'd be either 0.98.
Right, so it's in the middle, you don't interpolate, so someone will pick the lower value, the other one will pick the bigger value, and so Levin has to be a little bit tolerant in the, not really, Surrender will be tolerant because he's doing the quizzes, but Levin will be very tough because he's assuming you have the program. So Levin will be, you will hit Levin and you would love Surrender because Surrender would be a little bit nice on that number, final number. What I'm saying is that if you interpolate, you will not get exactly the same result because one of you will get the lower value, the other guy will get the bigger value. Because you are not really interpolating, you're just picking the closest value. Anyway, give me T over T naught.
0.9886.
0.9886.
886.
And P over P naught?
0.9607.
9607. And you notice that, wow, those are almost close to 1. Why? Because the Mach number is 0.25. Right? So actually, the magic number, if there is a magic number between, let's use a fluid 1 stuff, is Mach number 0.3. So when Mach number is 0.3, they think, well, the flow is like almost incompressible because they don't see that much change. Huh? So it's okay, it's just like, let's assume it's incompressible. So they will assume that the pressure, basically, the density does not change. But you can see as you push the Mach number beyond that point, the pressure and temperature will change so much that the density is not 1.2 anymore. Right? So anyway, so knowing P naught and T naught, you guys can get T and P, right? And so back again to the equation for M dot. You can get M dot. And I would like to stress again that when you look to when you try to solve those problems, you should solve it from the middle, kind of like, what is the main equation? How am I going to get my M dot? But once you have the idea that, well, it's rho EV, how am I going to get my rho EV? Well, I have to get the density, and then I have to get the velocity. And then you will say, well, how am I going to get my pressure and temperature? Then you would say, well, I need those conversion. So now once you laid out the plan, the solution actually will start writing it from here. You will say, well, let's start. I have the Mach number, here is T over T naught. Therefore, here is T. I have the pressure, and I have B over B naught, here is the B. And then you go one step up and then, well, here is the acoustic speed, and then here is the velocity, and then here is the density. And then finally, here is M dot equal rho EV. All right? But to think about the solution, you have to start from the kind of the end, what I want to reach at the end. Questions? All right. So here, C is when you see in the solution basically something like this, you can do this in the exam and the homework too. It's basically, what do I mean by this?
It's just from the table.
Right, I'm saying Mach 0.25, appendix P, let's give P over P naught. And so when we are grading the quizzes and the homework and this would be equivalent, making an arrow like this and putting B on top of it, that would be equivalent to writing the equation for P over P naught. It's equivalent to writing P over P naught, or P naught over P is 1 plus gamma minus 1 over 2m squared to power gamma minus 1. You do all this by saying an arrow with a B on top and say P over P naught equal to this. Right? You don't write this arrow, you don't write the B, and we have no idea what equation did you use. So if you just imagine if you actually had this and you screwed up this number, we have no idea where did you get that number, and you lose even the point for writing the equation. Of course, if you get the number right, then you can prove that you used the right equation. But what I'm trying to say is that to make your solution readable, you need to show us basically which equation did you use. All right? Very good. And consequently, of course, then not only you get P over P naught, but you can also get, P over P naught and T over T naught from the same appendix at the same Mach number. Right? Very good. Same problem, but different fluid, different gas, helium. So you say gamma 5.3, then that's not the right table. P1 is only for 1.4. Which table is for 5 over 3? Huh? 3, P3. All right. So now back again to our quest. Our quest is to get the Mach number, pressure, and temperature at different area in the pipe or the nozzle. Right? We are missing one equation between the Mach number and the area. Then our problem will be over. So, can anyone give me some help? How I'm gonna get this relation? How I'm gonna get relation between the area and the Mach number? So the physics of the problem is what exactly? So things are changing because the area is changing, right? Mach number and consequently pressure and temperature are changing because the area is changing. What is not changing between those sections? The flow rate, m dot. M dot is the only thing that's fixed between those different stations. The same kilogram per second is the same in every place. So the solution comes from this fact. So by saying that m dot is the same and writing m dot at two locations, for example, you will be able to find the relation between the two areas and the two Mach number. Because when you think about it, but m dot is not just Mach number and area. There is also pressure and temperature and all those stuff. But all those stuff can be written in terms of Mach number and constant, P total and T total. So that's the solution strategy. Right? You don't have to worry about how he drives this equation. But it will really help you to understand, but it's not that you will not be asked to repeat this. But basically he said, well, here's m dot rho EV, let's do rho EV, P over RT, and let's do the VMA. And then let's take out the Mach number, let's take out the T and the B in terms of B total and T total. So now this is the same equation, m dot rho EV, but now in terms of B total and T total. So this equation, there's only two variables in this equation, area and Mach number. That's the only two things that change. Everything else for this particular nozzle, same B total, same T total, same gamma, right? So he will write it at the throat. What happened at the throat?
M equals 1.
Right. That's the second most confusing thing for students in this course. So that m equal 1 at the throat. Is it always m equal 1 at the throat?
No.
No, right? Because let's put B atmosphere at one side, the exit, and let's have B atmosphere on the tank. B atmosphere, B atmosphere. What's the Mach number in the nozzle throat? right? There is no flow. Let me just increase the pressure in the tank a little bit. Let me put 1 Pascal. You think the flow suddenly will jump supersonic in the middle? Right? It take really big difference between the inlet and outlet to get supersonic. So what I'm saying is that not every single convergent divergent nozzle will have supersonic flow at the exit and sonic at the throat, depending on the pressure. But for sure, if the flow is supersonic at the exit, then for sure you can bet your money and your career and your job on the fact that the throat is Mach equal 1. If there is supersonic at the exit, then the throat cannot be anything but 1, Mach equal 1. Right? So over here he's basically saying, so now here's the confusing part, the second confusing part after the stagnation and static stuff. What is that area? So see, he took this equation and he said M equal 1 and A equal, area throat equal area star. So the area star, that area star is the area when the Mach number equal 1. Okay? So area star is the throat area when the Mach number equal 1. So if you have supersonic flow at the exit, then this Mach number at the throat is definitely 1, and whatever the 5 centimeter square here, that's area star. But if you see a flow that's not supersonic at the exit, because the pressure is not much, like 100 kilopascal, 101 kilopascal, that's not much, and the Mach number here will not be supersonic, and that throat area is not area star. What is area star then? Well, it's the area that will make the Mach number equal 1 at the throat, at those pressure. We will talk more about this later, but what I'm trying to say that area star is not always area throat. The throat area is the physical throat that when you buy this nozzle, you can measure it. That's the throat area. The area star would be the area when the Mach number is 1 at the throat. Okay? I think what you need to have right now is that the fact that you understand that they are not the same. They are not always the same. Now, when exactly they will be the same or not, we will explain this later. Next week too. A little bit today and a little bit next week. But at least you got the idea that there are two things that, like B static and B stagnation. Will B static and B stagnation be the same? Only when V0. So will area and area star, area throat and area star be the same? Only when the Mach number is 1. Okay? Right, so what happened then? So he got this equation, right? And he got this equation. Ouch. Which is exactly the same except for, that's not a good color, except for the Mach number become 1 and the area become area star. And then he divide the two of them. So if you divide the two of them, so what is basically this? This is like the Mach number at a certain area, somewhere in the nozzle. So you can imagine that the green basically represents something like this. And the what is that color? Is it pink? Yeah, fusion. That's basically this place. Okay? When the area is area star and the Mach number is 1. But between the two of them, they should have the same M dot, they should have the same B total, they should have the same T total. So if you divide the two of them, we are done. This equation is the relation between area and the Mach number, in terms of area star, of course. But basically, this basically tells you if the Mach number is 3 here, what should be the area of area star that will do this for you? No. Only if I ask you what is the Mach 1. If Mach equal 1, then area of area star will become 1. But if Mach is 3, How much area of area star will it take to make Mach 3? Let's say that we want to make a rocket engine that finish the last flow leaving should be Mach 3. What should be the area of our area star? No, we check Appendix P or this equation. So go for Appendix P. Open it for me and tell me for Mach number 3 what should be the area of our area star? Or area star over A or whatever he got. 4.2. Alright? So 4.2, that ratio, did you get 4.22? So 4.2 area exit over area star, that will make the exit Mach number 3. What if I would like to make Mach 10 at the end of the nozzle? What should be area over area star?
535.9.
Alright, didn't take much, huh? Just 5 will give you Mach 10. So now you can go back to the Saturn rocket engine and you can measure area exit over area star. Notice that the area is not the diameter, the area is diameter square. Right? So you can, from the picture you can measure the diameter at the exit diameter of the throat and get the ratios at like 10 times bigger, 5 times bigger, and then the area over area will be squared this to be 25. And then you can back it up and figure out, well, what is the exit Mach number that they had. Okay? Very good. So this equation, if you plot this equation, it will look like this. Alright? So what Chen was asking when I said what is the area ratio, and he said 1, it's when Mach 1 is 1. When the M is 1, area over area star become 1. See, when it's 1, when the Mach is 1, area over area star is 1. Of course, we know that. It will be 1 only at the throat, only at the star area. But then for area over area star equals 6, what's the Mach number? If you open the table, you will find out there are two values for that will do area over area star equals 6. Why there are two values? Did you find the two values first? For area over area star equals 6, there are two Mach number.
338
338 and 09, right?
Yeah.
Is that true?
Right.
One of them supersonic, one of them subsonic, for the same area over area star. How is that possible? Because which side, right? So you got the subsonic part and you got the supersonic part. So the same area can make you subsonic or supersonic, depending on which part of the stroke, which side of the stroke you are. Okay? But this equation is all what we need right now. So right now, just give me the area over area star. I can get the Mach number, and then I can get the pressure and the temperature. Bobby had a question? You got it? Right. So again, so now we know basically that the flow will accelerate into something like this, and then once he reaches that throat, will he become subsonic and decelerate again because the area is getting bigger, or will he hit Mach number 1 and start even continue accelerating as a supersonic flow in this place? It depends on this guy, the back pressure here. So that back pressure, so the back pressure is the pressure outside the nozzle. The relation between the back pressure and the reservoir pressure, or B note at the start, which happen to be B note throughout the nozzle, right? As long as this nozzle is isentropic, no friction in that nozzle, P note, P note, P note, P note, P note, P note, all the way. So the relation between those two guys, for example, if B back equal BR, 100 kilopascal, 100 kilopascal, what will happen? Zero everywhere, right? Pressure and temperature, P note everywhere. And once we start dropping this guy, once we start dropping B back, interesting things will happen. The flow will start moving. And if we drop it lower enough, we could actually get sonic speed here. And once we hit sonic speed here, depending again on this guy, we can continue as supersonic, or we basically go back again subsonic. Andrew had a question.
I think I'm jumping the gun.
All right. So B back, huh? Is it B exit? Is the back pressure is the same as B exit? The exit pressure and the exit Mach number and the exit temperature, those are the values, 1 micrometer outside the nozzle, just outside the nozzle. Or basically at the plane of the nozzle, kind of. Our B exit is the same as B back. Let me repeat the question again. So is B exit the same as B back? The exit pressure that the flow is leaving with, and the back pressure, that the pressure of the room where this flow is leaving to. Is it the same, or it can be different?
It has to be the same, just different velocity.
It has to be the same in fluid 1. But over here, the flow can actually leave without
No signaling.
without knowing what's going outside. He just leave and he said, oh, look at that, the pressure is really high. Let's basically, and he will start having those shock waves on him, or
But that's only if it's supersonic.
excellent. That's our division. Like, if he can see the chamber or sense the chamber, he must be subsonic. So subsonic flow will always be able to sense that chamber, and he will get B exit equal to B back. But once he's sonic, or worse, if he's supersonic, he will not be able to see the chamber. And he has no idea if the pressure there is high or low. So he will just come out, and we will go in detail. We'll see the detail in a second, all right? But first, an easy question. So he said basically airflow at Mach 0.6, so that's 0.6, and he would like to accelerate that flow to, well, later. Okay, in part first he calculate the mass flow rate through this channel. He gives us the static pressure, the static temperature, and he want m dot. What's m dot? Rho AV. And since we are given the static value, that's piece of cake. There is no, let's get B static from B total. No, it's already have the static value. So B over RT, and basically the V is square root of gamma RT. So again, let's remember that when it comes to the ideal gas equation, B equal rho RT, and when it comes to the acoustic speed, A is square root of gamma RT, what value are we using? The static or the stagnation? The static, the actual values. The value of the moving air. All right, so we got them here. Now part B, that's what's new. What percent of reduction area would be necessary to increase the flow Mach number from 0.8 to 1? You want to push the flow rate, the Mach number from 0.6 subsonic to Mach 1. So how can I solve that? The flow it's subsonic, 0.6. So it's obvious that if you want to accelerate a subsonic flow, what do you do with the area? Do you make it bigger or smaller? Smaller. So he's asking how small. Should I make it half the initial area?
Find A and then use.
The A is given to us, right?
Yeah.
No, actually, no, it's not.
No,
It's given. It's 50 centimeters.
Cross-sectional area.
But Chan is saying find the smaller A. What do you mean the smaller
Yeah,
one?
The, Mach,
I would go
B
to the
over A
table.
Mach number.
It has a name. It has a name. Area star.
Yeah.
It's called area star. So he's basically saying you have the 50 centimeter over here, find the area star. That area star is what you need to go to Mach 1. If you make the flow go to that small area, you will hit Mach equal 1. That by definition, that's area star. Okay? So how can I get that area star?
The table.
The table for this Mach number, right? For Mach 0.6 and gamma 1.4, there is area over area star corresponding to that. Okay, it happened to be how much?
For 0.6,
0.6 here.
1.1882.
1.1882.
1882.
That's area 1.
1.1882.
Okay. 1.1882. That's area over area star for that Mach number. So let's call it area 1 over area star. Area 1 over area star is 1.188. So you have area 1, that's the 50 centimeters. So area star would be a little bit smaller, right? You get that area star, that's what you need to go to Mach number equal 1. You got it? Okay, so area star, this actually work the same way like B total. You don't see B total in this problem, right? But I can ask you, calculate B total for me. What do you do? If I ask calculate the stagnation pressure here,
Go to the table.
you take that Mach number and you get what is P naught over P. From whether from the equation or from the table, but you are getting the ratio and you tell me that would be your stagnation pressure. Where is it? Well, if you slow down the air isentropically, we promise you will get that P naught. So it's the same thing for this pipe when I'm asking about A star. Where is it? It's not in that drawing. But at that Mach number, and you have this ratio, we promise you if you take this area and you reduce this duct to this new area star, you will hit Mach 1. Just like when you take that flow, that Mach number at that static pressure, and you slow him isentropically, you hit P naught. It's the same thing. So area star, sometimes it's not in the drawing, it's not in the geometry, but you can take the flow coming in this duct in front of us, and I can ask you, how can I send this guy to supersonic speed? Or sonic, let's start with sonic. How can I make this air go to sonic? You will go at that Mach number, probably 0.05 or something, and you will get area over area star, right, for that Mach number. And that would be the area star that if we take this duct and slow it, push it into that small tiny area star, he will hit Mach 1. Okay? Now, part C would be hard actually if let's answer the other one first. So what area reduction is needed to actually hit 0.8, not 1, just 0.8. You want to go to 0.8. How do I do that?
Take your same A star and calculate for A2.
Very good. And so what Bob said, to calculate the area that will hit me 0.8, he said that area star is the same area star for all of them. Just like P total, the stagnation pressure is the same for every place in the duct. They all have the same B star. Sorry, they all have the P total. They also have the same area star. This guy, area 1, the 50 centimeter at that Mach number, have this area star that we just calculated. It's also the same area star for area 2. It's kind of the reference state that all of them, if you take them to that area star, they will go to Mach 1. So he's saying that to get that area 2 that you want to get at, you want to have to in order to have Mach 0.8, he said at Mach 0.8 get area over area star. Well, that area star is the same that you had before, so it's as if you know it already. Actually, you know it already, and so from that you can get area 2. Does this make sense? That's not easy, by the way. That's every year, you know, until the midterm, people basically keep saying, well, why they both stations have the same area star? Why both stations have the same area star? Because where did we get that area star? It's coming from this. Well, the two stations have the same M dot, the same mass flow rate, the same B total, the same T total. So of course they have the same area star, as long as the flow between them is
Constant.
isentropic. As long as the flow between the two of them is isentropic, they have the same area star. They have the same B total. Now let's imagine for a second that we actually have a nozzle like this, and in here a local area of friction. You know, someone did a lousy job in polishing the wall, and in this place they have a lot of friction. The flow is not isentropic through this part. will P naught after the friction part remain the same as P naught before? Now that's easy to answer, right? No, it's not the same P naught. There's friction. Will the same area star remain before and after the friction? Excellent, no. For the same reason. Because if you change your P naught, if you change P stagnation between the two locations, because of the friction, the area star also will drop. Not that M dot will remain the same. That's not the reason why the area star is changing. It's because this calculation will yield two different area star depending on the P total, before and after. Alright? Will this ever happen in this course? Yes, it will. Because we may not have a friction at the wall. We are going to have, can anyone guess? Almost. We will have like really concentrated friction in one place, but we don't call it friction. It is a shock wave. A shock wave will happen, and that is tons of irreversibility. It cannot be reversed. Things really heat up and pressure drop, and so just before and after, two different stagnation pressure, we got that, but also two different area star, and that blew up the mind of few students. Like, what? How is that area star is different? Well, because
Everything's different. Just about everything's different.
only the B naught is different. Note that across the shock, actually T naught is the same. Amazingly, the shock is adiabatic. T naught is the same, and the mass flux, the kilogram per second, is also the same. So really, the only difference is the P naught. So B naught stagnation pressure drop, and basically the area star be different. All right, but this. I don't wanna jump ahead, but I would like at this point, while you are still comprehending that's the concept of area star, you need to know that it's not physically in front of our eye. It's just a reference state that when you take the flow to that area, he become area star. Sorry, he become Mach number 1. Andrew and Yang, you had the questions.
Okay, so I just wanted to validate my understanding of area star. So A star basically, say you're interested in like part B, a Mach number of 2.8. You would calculate it as if A star is a throat, even if you don't actually have that throat.
Right. Even if the problem just basically finish, like let me paint it in red. So the problem is like this, huh? The problem is just like 0.6, and you want to hit 0.8. There is no area star. He never asked about it. But the only way to get that new area 2, that you at Mach 2 equal 0.8, the only way to do that is to get to area star and then get area 2. And the cartoon that I always draw, and I will draw it for you 100 times in this course, I will always tell you, let's go get the star condition, and from that, let's go back again and solve for 2. That will be basically our philosophy in life in this course. We always go to get the star condition, solve for them, and then use this to get back again to the exit. We'll do this in chapters 3 and 9 and 10. So the star, it doesn't have to be in the problem, but it's in the equations. And Yang had a question.
I was just wondering, are we neglecting the length, the distance between A and A star?
Excellent. Yes. So Yang is saying, you didn't mention how many centimeters is that. It doesn't matter. The only thing that matters is the length is not important.
The area.
The area is. Why the length is not? How come the length is not important? Because we are assuming frictionless duct. So then it doesn't really matter if we kept going for a kilometer without friction and without heat transfer. It doesn't matter. It's the area. Did you reduce the area or not? All right? So I still have 7 minutes of your life. Where are you going?
We're leaving.
No, you have to wait. So let's finish. I want to finish with this because every year I finish with this. I want to finish.
Then why don't your slides in there?
So this is basically, let's have the easy part first, just the conversion part, right? And let's watch what happened to the flow, the Mach number and the pressure as we are dropping B back. So here is B reservoir. We said the reservoir pressure is the stagnation pressure, right? When you tell you the reservoir is 500 kilopascal, that's B stagnation. So if you have BR here and B exits equal to, or sorry, B back equal to B reservoir, what will happen? Nothing will happen. Everywhere the pressure is BR, the Mach number is 0. That's state number 1. Okay? That's state number 1. Nothing is happening here. Now let's take the pressure B back and lower it a little bit. What will happen? The flow will accelerate. Huh? The Mach number will go up a little bit. Not 1, but it will start, the flow will start going. And the pressure will drop a little bit. Not much, but it will. Eventually it become B, the B exit will become B back. Until the limit. The limit is when the pressure drop enough that the Mach number is 1 at the exit. Okay? Up to this point, this is one regime. Below this point, it's completely different. So at this point, what happened? The Mach number is, at the exit, is 1. Okay? And if I ask you what is the pressure that will do this, what is the back pressure that will do this? At Mach 1, if you open the appendix at Mach 1, that's the pressure there when you read B over B naught. This is called P star. Why it's P star? Because the Mach number is 1. So the area is, and this area now, this exit area, suddenly now it's called the area star. So before that point, that area exit was not area star. But at that point, that exit area is the area star because it managed to make Mach number equal 1, and the pressure is P star. That pressure, that number is, you will memorize this number in this course. It's 0.5283 for air. So when the back pressure was 0.5283, that is the magic number that will make the Mach number at the exit equal 1 and the area equal area star. So now what happens if I take the back pressure and lower it even more? Lower it than 0.5283 of P naught. So unfortunately, those were all the people before De Lavelle. That's what they were trying to do. They were trying to lower the pressure more and more, but they never managed to get anything faster than Mach 1 at the exit. This nozzle cannot get anything more than Mach 1, and that's weird. Why? Why if I keep dropping the pressure at the outside, why the flow wouldn't accelerate faster?
Because it adjusts to its new wave.
Because you cannot tell him. He can. You're right. You cannot tell him that the room just dropped at 1. So the example I would like to give is this. If you are going to an escalator, but the escalator is also moving down at the same speed, will you ever be able to go? So the waves are going inside, the pressure wave that basically tell the flow that the nozzle just, the chamber, the exit chamber just dropped lower and lower. It's trying to move at the acoustic speed. That by definition, they move by the acoustic speed. And the flow is leaving with the acoustic speed. So the information never really managed to go inside. So at this point, that nozzle is called what level? At this pressure, when the pressure, back pressure, is 0.5283 of P naught, this nozzle is choked. And reducing the pressure any more than this will not change the Mach number, will not change the mass flux. So basically from that point downward, even if you put the back pressure at 0, if you take this nozzle and you put it at space, this nozzle cannot get you any more pressure, any more flow rate than what it already did when it was 0.5283 of P naught. Okay? So we'll finish by this graph. So this graph is basically telling us that the m dot will increase, the mass flux will increase until this point, when the B back is B star, or basically 0.5283 B naught. And anything lower than this will not increase the Mach flow rate. So when he asks about the maximum flow rate, he's asking about the flow rate that you will get when B exit is B star, Mach number at the exit is 1, the area at the exit is the area star. That's the maximum flow rate. Questions? All right, thank you.